9.2 Series and Summation Notation. Warm up. Take a moment to work on this, then press play to see the answers. Okay, find the first 5 terms of each sequence. Well, for number 1, a sub n equals 1 divided by n, so we get 1, 1/2, 1/3, 1/4, 1/5. For number 2, a little bit of work I showed for this one, a sub n equals negative n squared. The important part is that the negative is not in parentheses with the n before it is raised, so all my numbers end up being negative, and my first 5 terms are -1, -4, -9, -16, and -25. For number 3, we get 2, 4, 8, 16, and 32. Objective: evaluate the sum of a series expressed in sigma notation. Sequence versus series. A series is the sum of all the numbers in a sequence. Because many sequences are infinite and do not have defined sums, we often find partial sums. And a partial sum, which is indicated by S sub n, is the sum of all the specified numbers of each terms of a sequence. So calculate the sum of the first 5 even numbers. So we go S sub 5 equals 2 plus 4 plus 6 plus 8 plus 10, which gets us 30. Summation notation, which uses the Greek letter sigma, which is capital sigma, to denote the sum of a sequence defined by a rule as shown. So we have the sum, which is what sigma stands for, from the first term to the 5th term of the explicit formula 2 times k. Example 2. Expand the series and evaluate. We want to know the sum from 1 to 6. So what we're going to do is we are basically going to take, and we're going to go 1 squared minus 10, because that's the first term, plus 2 squared minus 10, that's the second term, plus 3 squared minus 10 for the third term, plus 4 squared minus 10, that's the fourth term, plus 5 squared minus 10, that's the fifth term, plus 6 squared minus 10 to represent the 6th term. Okay, so the bottom number here, k equals 1, that says that's our starting point. The top number, the 6, that represents our ending point. And we add all of these up. So 1 squared minus 10 is -9. 2 squared minus 10 is -6. 3 squared minus 10 is -1. 4 squared minus 10 is 6. 5 squared minus 10 is 15. 6 squared minus 10 is 26. And we get 31 for our sum. Example 3. Expand the series and evaluate. We're finding the sum from 2 to 5 of 1 over 3 to the power of k. Well, that's equal to 1 over 3 squared plus 1 over 3 cubed plus 1 over 3 to the power of 4 plus 1 over 3 to the power of 5. We get 1 over 9 plus 1 over 27 plus 1 over 81 plus 1 over 243. Getting a common denominator, 1/9 becomes 27 over 243. 1 over 27 becomes 9 over 243. 1 over 81 becomes 3 over 243. Then we carry down the 1 over 243. Adding it all up, you get 40 over 243, and that represents your sum. Example 4. Write this series in summation notation. So now we want to write it like our previous examples were written. Well, the first thing we have to do is write our explicit formula, or the explicit rule. So to get from 4 to 8, you have to add 4. To get from 8 to 12, you add 4. 12 to 16, you add 4. And 16 to 20, you add 4. Because remember, 4 is the first term, 8 is the second term, 12 is the third term, 16 is the fourth term, and 20 is the fifth term. So to get from term to term, we have to add 4 each time, giving me the explicit formula of a sub n equals 4n. because you just are doing 4 times whatever the term is. So now, our summation notation, we have to write sigma, and we're going from k equals 1 to 5, because it's the first term to the 5th term, and our explicit formula is 4k. So instead of writing n's, we now write k's for summation notation. And that's your answer. Example 5. Write the series in summation notation for sequences with alternating signs that, like we have in this one. You're going to use -1 to the power of k plus 1 if your first term is positive, or you're going to use -1 to the power of k if your first term is negative. Our first term is negative, so we know right off the bat for our explicit formula, we are going to have a -1 to the power of k, or n. K and n mean the same thing. It's just referring to the term. So now we got to look. While our first term is 1, our second term is 1 over 4, our third term is -1 over 9, our fourth term is 1 over 16, our fifth term is 1 over 25, and our sixth term is 1 over 36. Keep in mind that if you look, our second term, our denominator is just 2 squared. For our third term, the denominator is 3 squared. The fourth term, the denominator is 4 squared. That means our explicit formula will be 1 divided by whatever term it is, k squared. So now writing summation notation, we have capital sigma, k equals 1 to 6, because there's 6 terms, and it's -1 to the power of k, that's how we get the alternating signs, times 1 over k squared, and that's where our fraction comes from. Challenge number 1. See if you can come up with a shortcut for the following series. We have the sum from 1 to 60 of 4. So take a moment and see if you can figure it out, then press play to see the answer. Well, this is saying you're going to do 4 plus 4 plus 4 plus 4 plus 4 60 times. You're adding 4 60 times. Well, remember, repeated addition is multiplication. So really this is 60 times 4, which is 240. Challenge 2. See if you can come up with a shortcut for the following series. We have the sum from 1 to 8 of k. Take a moment, pause the video, then press play to see the answer. So what this one's wanting you to do is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus all the way till k equals 8. Well, you can kind of combine numbers to make this a little bit nicer. So 1 and 8 gets us 9. So 1 plus 8 plus 7 and 2 gets us 9. Then we have 6 and 3 gets us 9. And then the 5 and 4 also gets us 9. So we end up with 9 plus 9 plus 9 plus 9, or in other words, 4 times 9, which is 36. Now, this might not necessarily be a shortcut. I'll show you the shortcut, though, in a couple slides. Challenge 3. See if you can come up with a shortcut for this following series. And if you have paper notes, you can probably see the shortcut right next to this slide. So that's kind of what I'm going to use versus going through this the long way. Because the long way would be to do 1 squared plus 2 squared plus 3 squared plus 4 squared and so on and so forth. And that can take up some time. So let's use the formula that's on the next slide. The formula that's on the next slide for a quadratic series is n times n plus 1 times 2n plus 1, all divided by 6, where n is the 12 up on top. So we'll have 12 times 12 plus 1 times 2 times 12 plus 1, all divided by 6, getting us 12 times 13 times 25, which is 3,900 divided by 6, which gets us 650 for our sum. Now, can you do this without knowing the formula? Yes, but it will take some time. So I suggest memorizing the formula. So summation formulas, when you have a constant series, you do n times c. N is kind of like your upper limit, the larger number that you're adding to. Okay. For a linear series, when you're taking the sum from 1 to n of k, you do n times n plus 1, all divided by 2. And for a quadratic series, which we just went through an example of, you do n times n plus 1 times 2n plus 1, all divided by 6. Yes, you will want to know these. They'll make your lives much easier when going through the homework. And that concludes the 9.2 lesson.